हाँ स्टार्ट.
Good morning everyone. Today I am presenting the PPT Microstructural Influence on Bending and Shear Strength in Aerospace Materials, exploring the invisible forces that define aerospace innovation, the critical role of material microstructure in aerospace design. So, in aerospace engineering, materials failure is not an option. The performance of components under the extreme conditions, such as high stress and temperature, directly correlates, and with their internal structure, their microstructure are shown in that critical role. Then, understanding bending and shear strength core concept. So there are two strengths are there: bending strength and shear strength. Bending strength is a flexural strength, is a material ability to resist deformation under bending loads. It's crucial for components like wing spars, landing gears, etc. All of this. Then shear strength. Shear strength is a measures of material's resistance to forces that causes parallel planes to slide post and to slide past each other, thin to rivets, bolts, etc. All of this, and adhesive joints for aerospace assemblies. Key microstructures. Key microstructural features of deep dive in material composition. So there are three types, three components: grain, size, shape, phase distribution, and defect imperfections. Smaller grain generally increase for strain and hardness, one of those. Then phase distribution. The phase distribution, the type of amount and distribution of different phases. For example, like as a precipitates, alloys, and significantly affect strength, toughness, all of these. Defect imperfections. The defect imperfections usually follow and inclusions through microscopic and can act as strains, concentrators, initiating cracks, etc. All of this. Next. Then question is, how microstructure dictates bending strength performance? So bending strength is intimately linked to materials ability to deform elastically and plastically. The microstructure elements influence the several stages. So likewise, there are three boundaries: grain boundary strengthening, precipitation hardening, and work hardening. Grain boundary strengthening is also easily like fine grain structures, prevent dislocation movements, increasing resistance to plastic deformation, and enhancing bending strength. All of those. Then next, precipitation hardening. Precipitation hardening is the secondary phase with the matrix creates obstacles for dislocations and significantly boosting yield or ultimate bending strength. Then work hardening. Work hardening deformation process like rolling or forging influence changes in microstructure, increasing some dislocation density and then improving bending resistance likewise. The next slide is the micromechanics of shear strength in aerospace alloys. There are three alloys: dislocation mobility, phase interfaces, and critical structure. So in dislocation mobility, examples are only solid solution strengthening or fine precipitates. The materials with lower dislocation mobility are due to solid solution strengthening, and for fine precipitate exhibit the higher strength. The next is phase interface. The phase interfaces, the strength of integrity of the between different phases are critical, or weak interfaces can be preferable paths for shear failure. Then crystal structure. There are many crystal structures like FCC, SCC, BCC, SCB. In fact, there are three crystal structures in atomic arrangement in the different crystal structures. Impacts the number and ease of slip systems directly to increasing the shear resistance. Then case study. Case study of aluminum alloys tailoring the microstructure for strength. The aluminum alloys are majorly used in the aircraft body, aerospace bodies, fuselage, etc. All of this. There are two types of alloys are common alloys are used in the aerospace industry. The aluminum alloys are used in aerospace to their high strength to weight ratio. Then next is advanced materials, composites, and their micro architecture advantage. There are three types of advantages: fiber orientation, matrix properties, interfacial bonding, etc. So the fiber orientation, the alignment of high strength carbon fibers with the resin or matrix directly dictates the composite bending and shear strength. The next is matrix properties. The polymer matrix binds the fibers and transfer the nodes. In toughness, the adhesion to fibers are crucial for preventing delimitation and distributing stress effectively. And next is interfacial bonding. It is used only for fiber matrix interface ensures efficient load transfer, maximizing the utilization to the high strength fibers and preventing premature shear failure. Then next is designing for durability, optimizing microstructure in aerospace application. There are three applications: advanced characterization, computational modeling, additional manufacturing. These are the three applications. The next is then let's come to key takeaways. So future horizons, engineering stronger structures. So the future of aerospace materials is lies in our ability to precisely control and engineer microstructure for unparalleled performance and safety. There are three structures. Microstructure is micro performance, continuous innovation, and integrated design. So, the aerospace components operates under the immense stress where even microscopic details can dictate success or failure, etc. The internal alignment of material, its microstructure or directly governance, its bending and shear strength, critical properties for aircraft spacecraft gravity integrity. This is a turbine wing. The example of the aerospace industry, which alloy and which structure usually start. Let's then fundamentals of bending and shear in material science. Then the impact of microstructure on shear strength in deformation, texture endoscopy, phase interfaces, dislocation movement. There are the deformations. This is the synergistic effects diagram. How microstructure influence both simultaneously. So the defect density are shown in the first column. Then next is improved shear strength, and last is over material toughness, grain size, and enhanced bending strength, etc. Then next is case studies. Aerospace failures and success linked to microstructure. In kind, usually the failure fatigue crack or commercial aircraft, in the commercial aircraft, the component failed due to fatigue tracks back to microscopic inclusions. And then let's come to aerospace failures and success into microstructure, fatigue crack and advanced aluminum. So first is commercial aircraft component failed due to fatigue tracks back to microscopic inclusions and unfavorable drainage structure that promoted track formation and cyclic loads. The next is advanced aluminum. New aerospace aluminum alloys achieve the superior strength to weight ratio through precise control of precipitate size and distribution, optimizing both the bending and shear properties for gliders from the aircraft. There are the advanced characterization technique for microstructure analysis. There are four techniques: scanning electron microscopy, transmission electron microscopy, X-ray diffraction, and electron backscatter diffraction. So the scanning electron microscopy provides high resolution images of deformation and fracture hands and to revealing grain morphology and defect distribution. Next, transmission electron microscopy. It allows visualization of internal structures at the atomic level, including dislocations and precipitates. Then, X-ray diffraction. It is used to determine the crystallographic texture, grain orientation, and identify phases. Then, electron backscatter diffraction. Maps grain orientation and boundaries, crucial for understanding plastic deformation. It is used for that. Right? Then, thank you.